We're going to learn about radical functions and basically how to graph those functions. So we've been dealing with radicals a lot, and we're going to use those tools that we've used on how to evaluate radicals to figure out how we can go ahead and graph those radicals. So first of all, we're going to clear up a couple of things. So basically, a radical function is any function whose rule contains a radical expression, right? So anytime you have an f of x equals something with a radical in it, it's considered to be a radical function. And we have been most familiar with the square root function. It's basically just a radical function that involves the square root, right? And we've learned about these types of functions before, but mostly in the context of the fact that we talked about it relating to the fact that x squared, the quadratic function, and the square root of x, the square root function, must be inverses. And a long time ago, in the beginning of the year, when we talked about inverses, we said that inverse functions represent a reflection over the line y equals x, right? And we said, all right, this reflection is one of the ways that we can determine values for the inverse functions, or determine whether or not functions are inverse functions. Or we also said this reflection was one of the ways we could determine if the inverse function would be a function itself. So the way we're going to talk about today, we're going to start by looking at our original functions, and then talking about the root or the radical function as its inverse, as its reflection. So on the graph below, you see I have the line y equals x. It's the red line. And I've already graphed the reflection of our squared function. But basically, I want you to see that right here, that if we were to go ahead and graph x squared, now if you don't remember what x squared is, it's a parabola. Its vertex is at 0, 0. If you want to make a table of values, you're welcome to do it, but I'm just going to go ahead and put a point at 0, 0. When I have 1, it's 1 squared is 1. When I have 2, 2 squared is 4, right? So I can kind of, you see, I'm like putting these values on the graph. You know, you can think of them as graphing actual points, or you can think of them as, you know, basically just remembering what the parent function x squared is, and then it doesn't have any transformations on it. So if we took this parabola, which if I connect these points, you can see they do end up forming a parabola. And if I reflect it over the line y equals x, you end up with what we have here, this blue figure. Now, hopefully you'll remember from Unit 1 that we know that its inverse, this blue figure, isn't a function. And we know it from the original function because we gave it the horizontal line test. And it fails the horizontal line test, so that means the inverse won't be a function. And most of the reason we know that is because of this plus or minus in front of the root sign, right? In order for us to get the true inverse, we need both the positive side and the negative side, and that's what makes it fail to be a function itself. So generally, when we talk about the inverse of a quadratic, we are talking about just the positive side of the square root function. So just this positive side. All right, similarly, the cube root function, right, is the inverse of x cubed. And if you want to make, like I said, a table of values, you're welcome to do so. So basically, I just choose some small numbers, both positive and negative, that I can cube, and I plug those in. So if I cube 0, I get back 0. If I cube 1, I get back 1. If I cube 2, I get back 8. Right, so that's the first one that kind of gets a little bit bigger. And if I cube negative 1, I also get back negative 1. And if I cube negative 2, I get myself back negative 8. So it kind of looks like they're just going to connect nicely, almost in a line, but they come up, and we know about this whole triple root deal, which is why we have this bend. This graph does have a triple root at 0, hence why it bends at 0. So here we have the cube root function, and you can see pretty nicely, here's the line y equals x, and so there's the inverse of it, and hopefully you can see these points over here come over here, and this reflection should be pretty obvious. All right, so how do we take that and we kind of graph it? So I'm going to teach you both ways. I'm going to teach you by making a table of values, and then also by just thinking about it in terms of transformations. So to make a table of values, right, we've got a table that we're going to pick numbers for, and we're doing a square root. So personally, I always like to think about numbers that it's possible for me to take the square root of. So what values can I easily take the square root of? Well, I can take the square root of 0. I can take the square root of 1. I can take the square root of 4. I can take the square root of, the next one would be 9, right? So I can take the square root of these numbers pretty easily. I can't take the square root of any negative numbers. So I've got to make sure that I don't end up plugging something in for x that would cause me to take the square root of a negative number. All right, well, knowing that, these are not the numbers I'm going to plug in here, because the numbers, when they get plugged into this function, right, these numbers, when they go in here, they're going to have 3 taken away from them. So that's going to cause me to think about better numbers, right? So really, I want this entire thing, I want this entire expression underneath the radical to equal 0 and 1 and 4 and 9. So what value could I plug in for x that would make it equal 0? Well, I could make it equal 3. And if I plugged in 3, I would get back 3 minus 3, which is 0. Square root of 0 is 0. And we always want this value. When you're graphing a square root function, you always want to make sure that you are going to get a radicand that equals 0, because that's going to be the starting point of your radical. All right, then we want to pick another number for x that would make it equal 1. So if I go ahead and I plug in 4, that would make the radicand 4 minus 3, 1. And if the square root of 1 is just 1. So here's my next value. What number could I use to make it 4? That would be 7. 7 minus 3 would give you back 4. So if I plug in 7, I'm going to get back the square root of 4, which is just 2. And then finally, when I plug in 9, when I want to get back 9, I would need, I believe, 12. And it's not going to fit on my graph, but 12 minus 3 would give me back 9, and the square root of 9 would give me back 3. All right, so if I go ahead and plot these points, over here at 3, I get back the value of 0. 4, 1, 7, 2, and then all the way out here at 12, I'm going to get back the value of 3, right? So hopefully you see that it's going to start here. It's never going to go past here, because I can never plug in a number that would cause me to get a number less than 0 here. So I'm going to start here, and I'm going to connect these dots. I'm going to make sure it doesn't look like a line. It kind of looks like a nice curve, and it goes up to the right. All right, so the domain, right? What value were we able to start with? Well, we were able to start with 3, and we included 3. And it looks like I could pretty much keep plugging in any number to the right? Any value of x to the right, and I would still get values. And how about my range? Well, it looks like the lowest number, this point is really important because it's going to tell us a lot about domain and range. The lowest y value that I was able to get back was a 0, and it's going to go up towards infinity. Whoa, that's a really crazy looking infinity sign. But from 0 to infinity is my range. All right. So going ahead with the next one, we've got a cube root. I've got another table of values, right? And so let's kind of talk about values that you can take the cube root of, right? Well, you can usually take the cube root of values like 0. Cube root of 0, I know that's 0. Cube root of 1, I know that. Cube root of 8, right? And then you can also do some negatives, because you could take the cube root of -1, and you could take the cube root of -8. So once again, we don't want to necessarily just plug these numbers in. We want to get it so that our radicand becomes one of these numbers when we choose values for x, because those numbers are numbers that we can easily take the cube root of. So we're going to go ahead. What number would make it 0? Well, hopefully you realize that that would be like a -4, right? So if I plug in -4, it would be -4 plus 4, which is 0. Cube root of 0 is 0, but then I've got this 4 on the outside. I have to multiply it. 4 times 0, okay, still 0. All right, what number could I plug in to make it 1? Well, I could plug in -3. -3 plus 4 is 1. The cube root of 1 is 1, and 4 times 1 is 4. All right, what could I plug in to make it 8? I believe that is just 4. If I plug in 4, 4 plus 4 is 8. The cube root of 8 is 2, and 2 times 4 is also 8. All right, how about my negative 1? I believe if I plug in negative 5 plus 4 is negative 1. The cube root of negative 1 is negative 1. And 4 times negative 1 is negative 4. And then finally, if I try to make it negative 8, I'd have to plug in negative 12. And I'm going to go ahead and I'm going to get negative 12 plus 4 is negative 8. Cube root of negative 8 is negative 2. And 4 times negative 2 is negative 8. All right, so this turns out to be that most important value. Most of the time, it's making the radicand 0. That's the most important value because it's the one I'm going to look for most when I go ahead and look for your graph. So over here at negative 4, 0, that's going to be the place where it does the little bend. Negative 3, 4. So over here, negative 3, 4 is, I believe, right up here. And 4, 8. Over here at 4 and up here at 8. And then finally, negative 5, negative 4. We got that value. And negative 12, a little off the screen and down here. All right, so what does this look like? This squiggle, if I connect these values, looks something like this. And when I go ahead and grade you on this, I'm really going to be intrigued as to whether or not this point right here is in the correct place. Obviously, you don't need to add that circle because it's not important, but that's what I'm looking at. All right, so what's my domain here? Well, domains for cubics are a lot easier than they are for square roots because it looks like I can plug in any numbers, positive or negative, and get whatever I want. So I can get a domain of all real numbers. And also my range, it looks like, hey, I got some 0, I got some positive numbers, negative numbers. My range is also going to be all real numbers. All right. So why don't you go ahead and pause, write down these two problems, and see whether or not you can pick some great values for those tables. We might look at those at the beginning of next class. In the meantime, I'm going to go ahead and remind you about some of the transformations that we learned about. You do have this in your notes already, but we learned about vertical translations. That's when we add a number to the end of a function. The examples I'm giving you are for square root functions. They do the same thing that they did for our original functions, our absolute value function, our quadratic function, our polynomial functions. So adding those numbers on is exactly what you would imagine. If I add 3 onto the end of my function, my square root function, I move 3 units up. If I minus 4, I move 4 units down. Moving things right or left always occurs in with the x. In this case, for our radical functions, in with the x means under the radical sign. So moving something to the right 2 units is going to happen under the radical sign directly to the x. And so minus 2, remember we said everything that happens under the radical is the opposite of what you would think. Minusing 2 moves it right, adding 1 moves it left. Vertical stretches and compressions, right, is when we take our whole function, we multiply it by an a. We just did an example with that with the 4. And so we have stretched it vertically. Everything that happens outside of the function is what you would think. So 6 times the square root is a vertical stretch of 6, whereas 1/2 times the square root would be a compression of a half. The horizontal stretches occur directly to the x. Everything that happens to the x is the opposite of what we would think. So it's actually the reciprocal of what you think. So right here, if you have 1/5, that means it's actually horizontally stretched out by 5. But if you had a number like 3, it means it's actually being horizontally compressed by 1/3. Finally, reflections can happen either over the x or over the y. If you reflect something over the x-axis, we're going to change all the y values to negatives, right? That should hopefully make sense to you. And so we're going to put that negative outside the radical. And if we're going to reflect it over the y-axis, we're going to put that negative inside the radical. All right, so how do we transform it? By using our functions. Well, we can make a table of values. I put tables at the below, right? But if we know our transformation rules, we know that we're going to take this regular square root function and we're going to minus 2. Hopefully we are aware of the fact that this has happened outside of the radical. It's minus 2, which makes sense. So this will move it down. It would help if I type the right word, down 2. So if you have your parent function on your graph already, so here I already have the parent function, I can take these points and I can move them down 2. So that 0, 0 point moved down to 0, -2, right? And that right here on the square root function, the next number, or I could take the square root of 1. So I have a value at 1, 1. If I move it down 1, down 2, it's now at 1, -1. And I had a value over here at 4, 2. If I move that down 2, it would be at 4, 0. So hopefully you can see that with a few points and knowing our transformation rules, we can shift that entire function down. And if it's easier for you, you are welcome to say, all right, we'll pick the same values we just did, just like we did on the previous example. So I would pick x is 0, I would pick x is 1, I would pick x is 4, and then I would go ahead and I would get the y values just by computing that. The square root of 0 is 0, minus 2 is -2. The square root of 1 is 1, minus 2 is -1. The square root of 4 is 2, and 2 minus 2 is 0. Right, so we can get those exact same values just computationally if you'd rather. I'm just kind of show you what would happen with the vertical stretches. We're going to take the output value, the y value, and we're going to multiply it by this number in front. So when I had the height of, at 0, 0, the y value is 0. If I multiply 0 times 3, still 0. At 1, the height is 1. If I multiply 1 times 3, I get the value of 3. So now that second point's moving up quite a lot. At 4, the height was 2. So 2 times 3 is 6. There you go. And the next number I think we could take the square root of would be 9. At 9, the height was 3. 3 times 3 is 9. So that's going to come all the way up here. And hopefully you can see this vertical stretch. We want to make sure we don't make it look like a line, so that curve is really important. If you want to go ahead and pause the video, copy down these two problems. These would be great practice problems. And finally, this is just kind of a graphic of me explaining all of the rules in one go, all of the summary of transformations for square root functions. These also apply for cube root functions, and we'll practice both of those in class. But basically, we have a number outside of the root, whatever type of root, no matter what the index. Honestly, I could put the index of n here, and these would exactly be the same. The value outside the front, we'll talk about your vertical stretch. And if it's positive, so a stretch is always positive or positive no matter what. It can be a fraction, it cannot be a fraction. If it's negative, that represents a reflection across the x-axis. So we would never talk about a negative stretch. We have a stretch, and then the negative would mean a reflection. Inside here with the x, we have 1 over b, so it's the reciprocal of what you would think. This number, this b value, represents the horizontal stretch or compression. If b was negative, or if this fraction in front of the x was negative, that would represent a reflection across the y-axis. This value on the end over here, h, is the horizontal translation that we're looking left and right. It's the opposite of what you would normally think. And the value on the end, k, represents the vertical translation. So these are all things that you've seen before, and when we're in class and we're practicing, we're going to go ahead and be more specific about using these types of transformations to find out where our function would end up. And that is it.